Dear students, so we know that suppose x and y are any two non-linear spaces, and f from x to y is said to be a compact linear map only when for any open ball u in x, then f of u closure of f of u closure is a compact subset of y. Compact subset of y. So this is the definition of compact linear map. A map f from x to y is said to be compact linear when x and y are non spaces, only when for every open ball u in x, f of u closure is a compact subset of y. Compactness means it is complete and totally bounded. Also in previous class, we see that f is compact only if for any bounded sequence xn of x, f of xn has a convergent subsequence in y. Okay, now we are going to a theorem. That is, the theorem states that if k is any, let k fall in k, and f is in CL, f and g are in CLXY, f comma g fall in CXY or CLXY. What is CLXY? CLXY is the set of all compact linear map from x to y. Means f and g are compact linear maps from x to y. CLXY is the set of all compact linear map from x to y. Then kf, k into f, and g plus f or f plus g are fall in CLXY. So this is our first argument. When k is any number, k fall in k, f and g fall in CLXY, k is any non-zero scalar, then kf and f plus g or g plus f fall in CLXY. How? So the proof is heavily depends upon our previous arguments. That is, it is given f is in CLXY, means f is a compact linear map. F from x to y be a compact linear map. Which is a compact linear map means, then we know that f is compact if and only if for any bounded sequence xn of x, f of xn has a convergent subsequence in y. So let us secant xn be a bounded secant in x. Secant xn be a bounded secant in x means norm xn should less than less than phi alpha for some alpha greater than 0. Okay. Now we know that since f is in CLXY means f is a compact linear map, then there exists a subsequence xnj of x such that f of xnj converges to some y in y, where xnj be a subsequence of x. Okay, since xn be a bounded sequence in x and xnj be a subsequence of this xn, then f is in CLXY or f is a compact linear map, then f of xnj converges to y in y. Since f of xnj converges, surely k into f of xnj. K into f of xnj also converges to some ky in y. K is any scalar, so ky also fall in y itself. So k f of xnj converges to ky, that again fall in y. That means this, according to the previous arguments, then kf fall in CLXY or kf is a compact linear map. Why? Because this kf has a convergent subsequence in y. Okay. So when f is a compact linear map, then its scalar multiple, the scalar multiple of f is also a compact linear map. Agree. Now also consider that f and g are in CLXY, means f and g are also compact linear map. F and G are also compact linear map. Now we have to show that this F plus G or G plus F is also a compact linear map. How? We know that is G following CLXY. Means G is a compact linear map from where to where? X to Y. Then there exists a subsequence set J of X and J. What is X and J? X and J be a sequence in where? What is X and J? Here X and J be a subsequence of Xn and the Xn be a bounded sequence in X. Therefore X and J is also a bounded sequence in X. Then we can find out another sequence J of X and J such that G of Zj which converges in Y. Let it converges to some small y in capital Y. That is G of Zj converges in Y. Okay. Zj be a subsequence of X and J, but X and J be a subsequence of Xn. So this should imply this sequence Zj be a subsequence of Xn. Okay, sequence of Zj be a subsequence of Xn. Sequence Zj be a subsequence of Xn. Then sequence J be a subsequence of Xn. Moreover, G of Zj converges in Y. Then what about F plus G of Zj? F plus G of Zj equals it is F of Zj plus G of Zj. Okay, F of Zj plus it is F of Zj plus G of Zj. Now consider F plus G of Zj equals F of Zj plus G of Zj. But we know that since F is in CLXY, Zj is a subsequence of Xn, surely F of Zj converges in Y as well as G of Zj converges in Y. So this should be converges to some Y or some Y1 in Y. That means this F plus G has a F plus G has a convergent subsequence in Y. That means F plus G fall in CLXY means F plus G be a compact linear map from X. So the addition of two compact linear map is also a compact linear map, as well as the scalar multiple of a compact linear map is also a compact linear map. Okay. Now we are going to another set. Let K is in K. F and J are the compact linear map from X to Y. Let F fall in BLXY. Before going to that one, that is let F is a bounded linear map. F is in BLXY and G is in BLYZ. G is in BLYZ. Then, and one of them is a compact, then GF is in CLXZ. Then GF is in CLXZ. One of them is compact. Either F or G is compact. Either F or G is compact. Listen here. K is in K. F is in BLXY. And G is in BLYZ. F is a bounded linear map from X to Y. G is a bounded linear map from Y to Z. That is X to Y. So F is a bounded linear map from X to Y. And G is a bounded linear map from Y to Z. Then consider GF, means consider the composition. G composition F. This G composition F, we have to show that this G composition F is a compact linear map from X to Z only when either F or G is a compact linear map. If one of them is a compact linear, then this is the composition G composition F is also a compact linear map. Okay, how to prove this one? So for let its proof is let Xn be a secant Xn be a bounded sequence. Be a bounded sequence in X. And let F is a compact linear map from X to Y. Why? Because from the argument or by the given hypothesis, one of them is a compact linear map. Here we assume F is a compact linear map and Xn be a bounded secant in X. Since Xn be a bounded secant in X and F is a compact linear map from X to Y, then by the previous theorem we know that sequence F of X and J has a convergent subsequence, which has a convergent subsequence in Y, which has a convergent subsequence in Y. That is, F of Xn has a convergent subsequence in Y. That means secant F of let Xn J be a subsequence of Xn, then F of Xn sequence F of Xn J converges to some Y in capital Y. Okay. Now what is G? It is given G following by where Y such. That is, G is a bounded linear map from Y to such. Since G is bounded, the continuity of G is preserved there. Since G is continuous, it is given G is continuous. So G is continuous means then G of F of X and J, that should be also converges to some Y following Y. Okay, some G of Y which converges in Y. Why? Because of that ensure the continuity of F. G of F of X and J is converges in Y. Since G of F of X and J, not converges in Y, it is converges in such. Okay. So if G following CL by such, G of F of X and J converges in such means this G composition F is nothing but a compact linear map. Again, instead of F, if G following CL by such, if G following BL by such, then by the same argument we can say that G composition F is also a compact linear map. Okay, thank you.